Welcome. So here's a question. It says a 2 kilogram block is stationary on an inclined frictional surface. It's really a frictional interface. It's both materials affect the friction, both the block's material and the slope's material, but we can call it a frictional surface, meaning there is friction there. And what is its normal force? So the first thing to do is visualize. There's a little diagram here. I don't like using the diagrams that are provided. I prefer to draw my own. And so I'm drawing my slope, and I'm trying to make the angle reasonably close to 30 degrees. The more precise your drawing, the better your work turns out to be. And then this is 2 kilograms, and I put the masses inside the blocks so that I can just glance and see what the value is. And of course this causes a downwards force of 20 newtons. Now the block is not accelerating, it's stationary, so it's not accelerating in any direction, and so this is in equilibrium, or we'd call it a statics problem. We can think about it as having for every action force there's a reaction force, so I can think about it as an upwards force, which is the reaction to the weight. But for these problems we prefer to divide up that force into two components, and we have a frictional force, which we'll call Ff, and we have a normal force, Fn. So these two forces are the components of the reaction force to this 20 newtons. Now, fair enough, we don't know either one of them, so how do we find the one we're interested in, which is the normal force? Traditionally, we could simply resolve all our forces horizontally and get an equation with two unknowns. We could resolve all our forces vertically and get an equation with two unknowns, and then from those two equations we could solve for Fn. But if we're a little bit careful, there is another way. And if I take this, and I'm just going to make this bigger so it stands out. If I take this, and if I want to ignore Ff, which is what I want to do, I want to only deal with Fn, then one of the things I can do is pick an axis which is perpendicular to Ff. This axis is at 90 degrees to Ff, and therefore Ff has no component on it. So fair enough. If I resolve my forces, if I find the components of the other forces along this line, there will be no contribution from Ff. Well, the Fn is straightforward. That's simply itself, because it's in the line. This 20 Newton, well, it's actually this force here. And this, I'm hoping you're getting to the stage where you can look at it and say, it's going to be 20 cosine of 30 newtons. And the way I got that was I recognized that this corner here is 30, which means that this angle here is 60 because it's part of a triangle. And if this angle here is 60, then this angle here must be 30 because that's part of a 90 degrees. So now I look at this triangle and I see that I have a hypotenuse which is 20, and I want the adjacent, and the angle between the two is 30 degrees. So the size of this component is 20 cosine 30. And so all that remains basically is to apply Newton's laws. So I say find Fn using the sum of the forces, let's say along the red line, just something to indicate to myself which line I used, is equal to 0. There's no acceleration along that red line, no component of acceleration along that red line. So the sum of the forces equals 0. Then I look at my red line. Let's make this end positive and this end negative. We've got to pick. So we can say, oh, plus Fn added to minus 20 cosine 30 is equal to 0. So Fn must equal 20 cosine 30. So Fn numerically is going to equal 20 cosine 30, and 20 cosine 30 is 17.32. 17.32 newtons. And yes, I'm ignoring the fact that I have a whole bunch of one-significant figure numbers lying around, and I'm just giving a couple of decimal places to help clarify the answer. So, first of all, we drew a diagram. Secondly, we asked ourselves, is this a physical situation that involves acceleration? We recognized it wasn't, and so we knew we were dealing with statics, what we'd call equilibrium. We then recognized we had two unknowns, and we elected to try to do it the speedier way of picking an axis carefully so that I can ignore the unwanted unknown. And if I want to ignore FF, because I want Fn, I draw my axis perpendicular to FF. It happens to be along the direction of Fn, but the real motivation is I want to be perpendicular to FF. I then look at my diagram, I recognize that Fn is along the line and that the 20 Newton weight is at an angle to the line. I figured out the angle. I recognize that the governing law was Newton's first law, and I wrote down my components, summed them, and found my answer. And there's my answer, 17.32 newtons. So there we have it.